Good evening, everybody. Good morning, everybody else on the other side of the globe. I would like to introduce Professor Spiegelhalter. Professor Spiegelhalter is in Berlin, which is fabulous. He's a German-born American architect and an associate professor and co-director of the Structural and Environmental Technologies Laboratory in the Department of Architecture at the College of Communication, Architecture and the Arts at Florida International University. He's also an engineer, a town planner, a principal of Thomas Spiegelhalter Studio and Associates, which has been running since 1990. Thomas Spiegelhalter has realized research demonstration work in Europe, Central and South America, in the US, in numerous contextual solar, carbon neutral, zero fossil energy, passive and low energy building realization projects. Large-scale sustainability, master planning and consultancy redevelopment projects for abandoned post-industrial architectures and landscapes. He was also part of engineering suspension bridges and revitalization projects. Now, the speciality of Thomas Spiegelhalter is in sustainability, carbon neutrality, and in that respect, he has performed. He includes in his master planning, in his BIM master planning, research and consultation projects, multiple sustainable measurement criteria systems, such as the European Building Energy Performance Certificate Methodology, UK BREEAM or LEED rating system, and the equivalent here in Germany. He has performed design and build research all over the world, I would say. And as a result of his 30 years or more of experience, Thomas has received more than 50 prizes, awards, and honors competitions individually and in collaboration with other engineers. His research work as a professor at FIU involves geospatial and climatic data repositories with AI-driven generative design workflows, mostly using BIM dynamic grasshopper coding with biomimetics. His current research is focused on optimized building and city design fitness tests towards carbon neutrality on a timeline from 2020 to 2100. Now, I would like to invite Thomas Spiegelhalter to the stage to present his thoughts on the anthropologic within his lecture, which he's sharing his knowledge with us. And his lecture is called Disruptive AI Data-Driven, Carbon Positive, Bio-Inspired Optimization Design Workflows 2020 till 2100. Thank you very much, Thomas, for being here, and the stage is yours.
All right. I'm just following the protocol of the CDC because I have to take 2 COVID-19 tests just to get back to the US. It's all disinfected. All right. Thank you for having me, everyone. And let's start. This is a 3-year research, actually, that is funded by EU Belmont and Horizon 2020 and NSF in the US. And I have a case study, a personal case study. It's Miami and the Greater Islands. in particular Miami Beach and the islands. So let's start. So disruptive AI, data-driven and carbon-positive workflows started already in religion with Bosch's most famous Garden of the Earthly Delight in 1500 and Kafka's Metamorphosis. And today we know that the global population is about shrinking since 1900 from 791 to 3. And then we have the first telephone in 1873, 2020. Now we have Elon Musk with the neural link. And this is some of the work I did in cooperation with Alfredo Andia, post-parametric automation in design and construction, which is already, it's gone. We are in another level at the moment. But it obviously starts and thinks about deep neural networks, AI data-driven planning, data mining, processing. And now we are going towards singularity and include climate adaptation and resilience and well-being, as we heard it from our previous speaker. And years ago, I looked at, I created this timeline, what the parametric workflows of tools are on the top, and below you see all these conferences and rating systems and how they evolve and how they are going to change with synthetic biology and deep neural networks, et cetera, towards 2100. And this is exactly the topic. So in this research, first of all, you always have to find out, where are we? How did we get there? So it's important to look at urban growth models, envision models, existing data repositories, using GIS, Panda, and GeoPanda and other tools to go into building information modeling and connect it to AI cloud algorithms and create a baseline where we are, in this case 2018, because we didn't trust the government, we didn't trust the city, what they have on data. We wanted to have our own data and then simulate and create scenarios that are different. So what we see here is Miami, and you see already some experiments that fed into design studios, experimental studios, and the children born in 2019 will experience in Miami storm surge. And I'm thinking here about the Dorian event in the Bahamas with 23 feet storm surge, and now at 8 to 10 feet sea level rise. So we are talking here about 30 feet of sea level rise. This will lead to a mass relocation of the population. Now we have the tools. You see here also an integrated decision support system that we are developing for citizens and planners and stakeholders to use a geocoded location on a smartphone and then go through those scenarios to see where we are. And here are some XML files of data processing that we then justified. Now, these are the tools that we are using for example, for high-rise typologies on stills that pay attention already to the 30 feet sea level rise. The infrastructure has to be elevated. And here we are including all these variables, right? Sun, solar, etc. And this is just an example how much will be flooded in Miami. Now, at the moment, we have a mass fish killing going on in the Biscayne Bay. So this stingray is trying to get the last sip of oxygen before they die. So I I could tape this stingray before actually it died, and then stranded on the island. These are remote islands, and you see me on the right side with my kayak in the background taking samples. And this is the system, this is the ecology that we are based on, that we are depending on. And here, this diagram shows you on the right side how we can learn from bio-inspired processes and think about programmable matter and how we can code this. Now, this is from Autodesk. Autodesk is running this cyborg research with BioNana, and it's all about life science. And this feeds into the architecture, engineering, construction, utilities, media, entertainment, automotive. And they offer a platform like this one where we can program matter. But what are the drivers for BioNano research, coding, and design?
What is it, life? What makes it different from just matter?
The robot voice.
Everything, living or not, is just chemicals made from atoms. These fish and the water that they're in are just soups of atoms. But what makes the fish alive and not the water is how the atoms are organized by a special kind of molecule. And you know this because you learned about it in high school, DNA. The double helix molecule that houses the chemical alphabet of A's and C's and T's and G's, which in different combinations can make a flower, or a frog, or you. Every living creature has its code that makes it grow, reproduce, and change. DNA turns dust into life.
The bulk of this tale takes place about 2.5 billion years ago at the end of the Archean eon that had started about 1.5 billion years before. This vast stretch of time included huge milestones for our planet, including the early days of the microcosmos.
So we are depending on these processes. And you see here the Biscayne Bay that is analyzed, benchmarked, diagnosed with sensors, millions of sensors in the air, in the water, and it's depending on oxygen. The question is, how can we keep oxygen until 2100? Here we see a data collection of our students from FIU, how they use the submarines and also above the water to figure out where are the particles, the runoff, the thousands of leaking septic tanks, the plastic, the nutrients, the phosphor that goes all into this open sewage system, which is the Biscayne Bay, as you see it here. And here again, the stingray. Don't forget, Miami is built on a sponge. It's floating on a sponge like this. So the question is, what comes next? And this also relates to food, water, energy nexus, because all these processes and systems are interlinked, are intertwined. We have to shift away also from the typical victim food production. No meat, going to plant-based diet, printing food, etc., program matter. And these are towers that we created with algae powered, etc., that give the people in these Miami Crater Islands the food that is printed and sufficient. Now, this means we have to go back to biochemistry and study. So building biology is not enough. We have to understand the chemistry
Was only just beginning.
to go towards the future.
We don't know quite when cyanobacteria emerged, just that it's sometime before 2.5 billion years ago. And when they did, cyanobacteria brought something new to the photosynthetic mix. They used light to split water into its chemical components, hydrogen, which could then be used to make other energy-storing compounds, and oxygen, which was released into the environment as a waste product. This simple chemical reaction is the source of the Great Oxidation Event, which you might also hear called the Great Oxygenation Event, an accumulation of oxygen in a previously anoxic world. That reaction would go on to become one of the most important ones to life, the source of the very oxygen you are breathing now. And remarkably, cyanobacteria were not just the first organisms to evolve oxygenic photosynthesis. As far as we know, on our planet anyway, they are the only organisms that do so. That we don't have the tools or physical evidence to even fully describe it, but life still managed to endure. And as it did, the oxygen produced by cyanobacteria would go on to form our planet's ozone layer, shielding survivors from dangerous ultraviolet wavelengths of light. Moreover, the availability of oxygen in the water and air would go on to make aerobic metabolism possible, providing organisms more energy than anaerobic metabolism ever could, and thus the capacity for more complex life.
So, towards carbon positive or carbon neutral infrastructural building and city system, there is no other way, no other future to think in complex, integrated ways and include the question of anything that we are designing today needs to be just optimized, and it needs to be benchmarked, and it needs to be fitness tested. So here we have this example of emitting technologies and carbon removal technologies that also deals with phytoremediation projects, which I have done, for example, with landscape architects in the Ruhr Valley for over 20 years. So the question of photosynthesis is important as well, bioremediation, and it's all intertwined. So designing buildings also means there's an output and there's an input. There's a flow, there's a process.
There are many gaps in our understanding of the Great Oxidation Event. Gaps built on unanswered fundamental questions like, how did photosynthesis even evolve? We alluded to one of the most important gaps earlier. It's the question of when cyanobacteria first appeared. And that question is key to understanding how they caused the Great Oxidation Event. If that event began shortly after the evolution of cyanobacteria and oxygenic photosynthesis, then it all seems relatively straightforward. The cyanobacteria produced oxygen, the oxygen.
So with this, it's also a design about oxygen, to keep the oxygen until 2100 and beyond. Now here we see some scenarios of Miami Beach below and these new buildings on stills. And we see here integrated simulation tools that look at the humidity and storm events. Category 5 goes to category 6, etc. And self-growing islands that are based on cyanobacteria that adapt to sea level rise, and so the structure is self-growing. And in the middle, you see this Autodesk Research Multicellularity tool.
Species form filaments of individual cells, a few of which even take on specialized functions like nitrogen fixation. These scientists trace the origins of that trait to before the Great Oxidation Event. So maybe multicellularity allowed cyanobacteria to not only better contend with the challenges of their environment, but to produce more oxygen than built on the available evidence, which means it is still subject to debate. But the seemingly simple question underlying it, the question of when cyanobacteria evolved, reflects what's so important about the Great Oxidation Event in general. That questions of biology, geology, and climate are so intertwined that to understand the history of this planet, we have to piece together the history of the microcosmos. And if something as small as cyanobacteria can set off a catastrophe.
So the microcosmos is the baseline in the biochemistry. Here we see this simulation that is looking at self-growing high-rise buildings that adapt to wind forces, to humidity, to solar radiation, and taps also into the infrastructure of Biscayne Bay. So in summary, we need to recognize the superiority of other forms of intelligence compared to the one that we are using at the moment. A revolution is already underway that places humanity in its appropriate environmental nexus, questioning our survival of oxygen or deoxygenation, as we see it already in Biscayne Bay. The sustainability of the biosphere is seen to be inseparably bound up with human development in a global and symbiotic system. As the evolutionary theorist and biologist Lynn Margulis has put it, we live on a symbiotic planet, not separated. And the 3.6 billion years only represents for humankind a 3/4 second. Only a 3/4 second. That's the time as we are here. And we have already destroyed over 80% of man-mals. So disruptive AI data-driven coding and design, carbon-positive, natural and synthetic biology-inspired workflows will spectate the embodied character of human and artificial intelligence. And this is the last slide, and you see here an integrated design that cleans up, like phytoremediation, the groundwater, the Biscayne Bay, it turns it into a biofuel, operates the building itself, as the building itself is a self-growing, adaptable skin and structural system as the mangroves. And humans play a pivotal role in this because it's about thermal comfort and well-being, as we heard before. Now, this is a very complex project, and I showed you only some of the best work. There are many, many players in this, and we will post the links. And it's also, in the moment in production, be published by Franco Angeli in Milano. We have Volume 1, Volume 2, and Volume 3. Thank you, everyone.
Thank you very much, Thomas. May I invite you to a little dialogue between us? The answer is yes. If you had said no, that would have been a disaster, right? Okay.
So I wanted to show you this as another option for 2100. If we don't understand what oxidation means, then we might need this in 80 years, probably. This is a Bioware mask, costs $220. And if we don't have oxygen, then we might need this. And these filters are replaceable, right? Tesla has this already in the cars. So we might need this. Or we can even 3D print them by feeding them with the appropriate variables of humidity, particulate matter 10, PM7, PM5, and all of them.
I think that's a scenario that is not so desirable. So thus we are here. Thus we are talking about the anthropologic, and it's always enjoyable to have a little bit of provocation, but as we know each other, it's almost impossible to provocate each other.
Liss, it's also about, I'm not sure if you guys know Paul Virilio,
yeah, of course.
Thinking by accident. You know, it's not the plan A. You have to think of plan B, plan C. So what if the AC fails or the HVAC fails in the airplane, right?
Yeah. Thomas, we had a bit of a pre-conference conversation, and together we developed a question that I would like to pose to. Actually, I put on some notes as well during your talk, but there's one question I would like to ask you. Of course, it starts with a little bit of a statement, and then there's the question. So, Thomas, looking at the system as an organism is the first thing. And here I also mean designing architectural and urban typologies that foster, for example, resilient and adaptive design or oxygen production, as in trees, or possibly also organisms that we don't even know about yet, or organisms that are deep within the sea and the oceans. Now, which components would you, as an expert in the field, integrate into the calculation? And this is where I'm looking at some kind of score of what carbon neutrality can be. I'm posting this question because currently we do have LEED, we have BREEAM, we have something which is called like the energy saving regulation law in Germany, which fosters the styrofoam industry, and I'm not sure if this is the way forward. So I would like to find an alternative to BREEAM, LEED, and all these things. So what would be your idea of which components could go into that score, into that calculus?
Well, most of them do not help and need to be revised anyway, because it's the biosphere is a very complex and dynamic system. And at the moment, when we look at synthetic biology, which is at test through the pandemic outbreak of bacteria, we hardly know what those represent and where do they mutate to. And that brings us back to these many rating and benchmarking systems. One of them is, for example, the new Well-Being Institute, which mostly includes everything that we heard from my colleague speaker before. But it's not a design tool. It is important that whenever we talk about carbon positive or carbon neutrality, and there will be more words coming up in the next years. In my last 30 years, there were many words for this: Nachhaltigkeit, sustainability, high-performance buildings. And I always asked, what is a high-performance building? Or what is a smart city? And I really never understood exactly what it is. You only understand when you start to look at trust and trustworthiness. Now, trustworthiness, in this case, means you have to collaborate with others who are experts in biochemistry, in biology, etc., medical biology, etc., and intertwine your research towards a baseline that becomes the beginning. And then you can start to optimize all these variables and include more. But without a baseline, any optimization is not adaptable for quick changes and dynamic changes. So this is very important. This is why I was always shocked when I moved to the United States about 21 years ago. And I had to do these short semesters. I couldn't believe it. How can you teach building physics or environmental systems in one semester? Or talking about steel or wood, and no building biology, no building chemistry tests. I studied in Germany, where we had one semester steel, one semester wood, and always integrated life cycle analysis with the Eco Institute in Freiburg, for example. There were some tools where we could look at life cycle. And the same applies for any product. We have to look at the life cycle and the impact on the environment. But again, we have seen in this presentation that the DNA and the bacteria, this is just a fraction what we understand, and more to come, to learn from and to apply. This is why I'm very fascinated that we have now the opportunities to use bio-nano programming and coding. And even if you shift from victim-based eating, like meat, to plant-based, this is a completely new study. Even for myself, in my age group, I have to study now food and read the labels and understand. But I have no inflammation anymore. It's gone. No inflammation for years since I shifted to plant-based food. And the impact is also astonishing. There is no cow standing in their output up to 2 meters or 1.50 meters and gets corn fat. And then the output goes into Biscayne Bay or in any agricultural groundwater or infrastructural system. This is the answer. It's a complex system. And we have to forget our degrees, our PhDs, our diplomas. We have to always learn and be open. This is why I like very much the keynote speaker this morning. He just spoke out of my heart.
It's wonderful, thank you. So there's so many thoughts in here, especially the complexity between, different kinds of ecologies, also the integration of political decisions, or how do you work with your cattle capital, I would like to call it. But more importantly, how do we deal with that in terms of architectural education? I think this is also one of the reasons. One of the reasons why we're here. I want to say that in a few minutes we are going to have everybody from this day on the stage, and some of the questions that pop up through the WebEx. I would like to point to you. I think the second or third question is in fact a combination between Lars and Thomas, so we keep this for later. But the question that we see now is for you, Thomas, considering the current trends of technology in architecture. Now, my comment is, what are the current trends of technology in architecture? But that's another question. How do you see the process of integration of data-driven architecture? Again, my comment, what is data-driven architecture? And utilization of biological practices. Again, the question, what does that mean? To be commonly accepted and be a norm in architectural practice and design workflows. So maybe before you answer that question, or before we discuss that question, can we keep this question for the roundtable for tomorrow? That would be amazing. Because in that sentence are so many things to define in the first place, so I'm not sure if one can actually answer that, but it's a start of a discussion.
To discuss this, we need a boundary of time, because
10 seconds.
Oh, yeah. I would say revolution.
Evolution?
Revolution and evolution. Because it's about trust and trustworthiness. First of all, any political statement, to bring in politics, like, the keynote speaker here, the first one might remember that the first anti-nuclear movement that was actually in Southwest Germany. And I was young at that time, I was part of it, where the farmers and the university mobilized and did participatory democracy with distributing and sharing information about nuclear power. And this is exactly how the solar movement started, right in this little triangle of Southwest Germany and Switzerland and Alsace, because there was a need. And the same might happen in Miami or in other places, or Black Lives Matter. This is important. We need to resist, we need to inform, we need to work on information, share information. We might even have to learn how to create bots and other AI and machine learning driven ways to inform the public and mobilize. It's very important. In education needs to be completely retooled. The way we teach at the moment and the curriculum is done, and how these rating systems in the United States, it's the NCAADe and the AIA, it's not enough. It's an alibi. It's not enough. We need to do more.
That's fantastic. Thank you, Thomas, because I think especially with that talk and possibly that sort of, the questions that we had from the audience, I think we do realize that we are at some kind of tipping point towards data, not towards data. What is biodiversity? Are we going back to the analog, like Rachel Armstrong was talking about today? There's the question about biodiversity, and one thing that I came across recently is a new protocol for data, which is called FAIR data, which is pretty much sort of free, accessible data that all disciplines can use. And the question of interdisciplinarity I would like to keep for tomorrow afternoon. And now we should take 8 minutes or something like this to have 5 minutes, 8 minutes to have a round table with the 5 of us. So I would like to invite Dietmar and Chris and also Lars, and have the assistants to have a quick change of the setup of the chairs so that we can keep the distance to each others. Okay.
Thank you.
So stay online, which is sort of having a little bit of a moving of the furniture.
For everybody, and also a long day. And we also have to remember that probably certain people are still joining this session, that it's kind of 3 a.m. in the morning or maybe 10 in the afternoon. I think with the Anthropocene, we have an interesting topic. And we have seen through the keynotes and also probably through the papers that there are diverse answers how to tackle it. Somehow it might be a wicked problem, like Riddle and Weber addressed it in '73 by their paper. Some people might refer already climate change as a super wicked problem. Nevertheless, I think it's important to start the discussion. And one overarching question somehow which went through all the keynotes for me was still that everybody's talking about algorithms. And these algorithms, I mean, the theory probably has been there since 100 years, but algorithms implemented, I mean, is just recently. And to make it simple, my question would be quite easy for everybody. What is your intention, how this might have changed, let's say, as interdisciplinary approach? Does it help algorithms, digitalizations? I mean, we can't go back anymore, but what are the benefits for it?
Should I?
Chris?
Yes, well, is this on? Oh, is it on now? Is it working? Is this one working? Okay, so yes, it's a very, very interesting question, Dietmar. I'm not quite sure how to answer. When you write algorithms in areas like fluid mechanics, for example, you find that if you change one line of code, or there's a mistake that you're not aware of in one line of code, you can get completely different answers. And the longer and more complex the code is, and the larger the number of variables, the more it's possible to get almost any answer that you may want from an algorithm. And it's very difficult to explain that to somebody who is not involved with them, because you sort of say to them, well, this algorithm says this, and therefore it must be true, whereas in fact, that doesn't necessarily mean that it's true at all. And I think when it comes to something important like climate change, we were talking about, that we have to find a way of demonstrating that what we're saying is true without relying on, or without relying solely and too much on algorithms, which are a sort of black box, which maybe will not convince everybody.
Yeah. I would like to add to Chris that it is very important to look how the algorithm is coded. And in practice, it's often the case that we start with a certain baseline, that's an XML file, and then we feed into platforms like, let's say, building information modeling, GBS or Insight 360, use a Cove tool or any other tools. And what we get is we get 3-4 different results. And why we do get 3 different results is because we need to double check how the code is written and what is missing, what kind of building codes, what kind of data sets are pulled in, what are they relying on, how old are they. Climate data, for example, you need to know that you have more than 3 years of data collection. And you need to have an agreement that everyone, from the engineer, the traffic planner, the health engineer, the doctors, the architects, everyone use the same weather station ID. If we don't use the same weather station ID, how can that be the same? So this is very important. And the same, imagine a structural system. If you use the wrong category, hurricane category 2 or 3 or 5 protocol, this is liability. It's all about liability.
And how, I mean, would you see then architecture in future? If I start studying architecture, do I need to become a programmer? I mean, what's about algorithm and creativity? So you say yes?
Yes, you have to learn the programming and coding and scripting language. And you will deal in the future with programs which writes themselves. They're writing themselves, and you become a, let's say, a topology conductor like in an orchestra. But you need to know the basics and the content what you want to achieve.
I think I would agree. As much as you want to enter architecture day in any forms, like practical work, if you don't know the software, you won't be picked. But I think we have to remember that the computer itself, let's say it's software or it's writing code and algorithms, it's just a very, very smart pencil. The pencil doesn't give answers. Somebody has to hold the pencil and do something with it. And there needs to be an intention. And that intention might be, good or bad. There's no truth in this. So in the end, education need to teach you today, and even before going to school, we have to start education. People coming out of school today, going to university and not being trained properly in order to be fit for what happens then when you really profound your studies in school. So I totally agree with that. But we have to remember it is just a tool. It's a very smart tool. But how you use it is up to you. What morals lie behind you doing is up to you, and that needs to be part of your education as well.
Thank you very much, Lars. Moving towards that subject of education, and there is that saying that I think all of us know. It takes a whole village to bring up a child. So, if we look into architecture, which I think has become extremely one-dimensional, right, these days. We talk about biomaterials, but we only look into simulations. It's very hard to build up a laboratory of algae and so on in an architect school, especially in these days. But that's a question kind of maybe even for Chris, because you're the most experienced one here. How many disciplines does it take to not educate, but to bring up an architect? In England, we would say, I'm born and bred in the Bartlett School of Architecture, right? But in Germany, you would never say, I'm born and bred in the Technical University of Berlin, because the born and bred is semantically different. In England, we would say that. But how many disciplines does it need, or do we need to become an interdisciplinaire?
Well, I suppose there was a time when an educated person knew pretty much all there was to know about everything. Now, of course, every separate profession tries to make sure that whatever it does is as difficult to understand as possible by everybody else, to ensure that you have to go to ask them about energy monitoring or whatever. So I'm sure that it's perfectly possible for a young person to know pretty much all they really need to know about everything to do with architecture. And one of the big problems, I think, is the difference between education and training. And that is that obviously we have to try and make our students employable, but that may well mean that we essentially just train them in using whatever techniques are required in industry. And this was a big issue in environmental engineering at the University of Bath. The industry was just saying, we want you to train your young people to just be productive on day one, the day they came into the office. And people like Max Fordham, I don't know if you know Max, had a very, very completely different view where essentially it was much more about education. And I think that's always going to be a tension in all disciplines.
We have one question from the audience. Might be interesting. Let's see. Should we answer to that? The question would be, combining your presentation with Lars, the healing effect of biomaterials and such, do you see potential in that? And I think there was, it refers to Thomas' lecture, right? Probably. Okay.
Combining your presentation with Lars, the healing effect of biomaterials, isn't that Lars? I can answer it too.
Combining your presentation with the ones of Lars, how do you see?
I would say absolutely, because the presentation I showed was more or less large-scale, complex, dynamic systems with very specific nano details, like how to produce oxygen or bacteria or self-growing systems, while Lars presented a practical example of a hospital and how diurnal lighting helps to stimulate our circular metabolism to achieve well-being. This is translatable to any level in architecture or engineering. This is fundamental. I mean, look at the natives. We can go back thousands of years. Our ancestors did live like that. And they worked less because they went to work after sunrise and they went to bed after sunset. Now we have electrical light, and now we're doing night shifts. And some people are throwing in certain pills, which then cause inflammation and other side effects. And then they end up in Lars' hospital.
I wish it would be my hospital. No. No, I think we can all agree as we sit here. I mean, the fundamental, I think, idea behind it or in the question is we always learn from nature. I mean, the great engineers looked at nature because there is no better engineering than in nature. Yes. You know, circular economy, you know, cradle to cradle, Bill McDonough and Michael Braungart. They're basically looking at nature, saying, it's like, can we copy nature in saying there's no waste in nature? There is none. So if we produce things, can we, in the end, when materials die, bring them back to the circle of life? So we all have to look much more closely to nature. Photosynthesis, I think you would be saying that, but I think it was implemented. Yes. If we would tackle what plants can do, just closely, the efficiency of photosynthesis, our energy problems would be gone immediately. You know, and it's a natural process, meaning we still have a lot to learn from what already exists if we look and learn closely. What I'm saying is, yes, let's go into biology because there are the biggest learning curves we can do, and there's a lot still to discover. I think it's an exciting moment. To be honest, I think it's a kind of a frightening moment, but it is an exciting moment at the same time.
Thank you very much, and I think it's also an exciting moment for us and the audience all over our spaceship Earth to look forward to tomorrow, to look forward to tonight. We are looking forward to dinner, I would say. And once again, I would like to invite everybody to join the Mos Eisley Bar, which is open. It's been open for a while. We do have a gig at 9 p.m. Berlin time, which is going to be a bit surprising for you guys. And we do have the most amazing gig at 11 p.m. Berlin time, which is going to be Jeremy Ham drumming, VR drumming to music that his daughter, who's a DJ in Melbourne, created. And this is going to be transferred to Stuttgart in Germany, where Uwe Werner is going to project it into the cave under his computer sciences department. So that's at 11 p.m. Tune into the Mos Eisley Bar in between, go there, chat, network, figure out some questions for tomorrow. And then I would like to close the session today. And we're going to see each other tomorrow, 9:30 Berlin time. In that sense, I would say have a great night, day, wherever you are. Thank you.